Hello, welcome back. This is Sylvia. So what I want to do in this video is the mother of all examples so that I don't have to spend so much time trying to get this done. I'm gonna do it cold and I hope I get it right. That's all I can say, but at least it's about the process, all right? So we're gonna do a 2-story frame, but it's gonna have all kinds of boundary conditions and connections and joints and things like that. All right, so let's make the boundary conditions be we're gonna have a fixed at one end of the column, and we're gonna have pinned at the other end of the column. We're gonna put hinges in this beam here, but a rigid connection here. The column is gonna span all the way up with a rigid connection here, and then I don't even know if this is stable, and a system that looks like this. Yeah, it's good enough. Oh, this is gonna be fun. I wonder if I can just uncouple them, but anyways, let me stretch that, draw this out just right. Just have to make sure that you know, you don't have a mechanism, but this is almost like a cantilever and it's fixed here, so I'm comfortable with this system. And then the system here, it doesn't matter because it's connected to that one, so I think we're okay, and it's not statically determinate. I'm gonna just make it that much interesting that I've got the eye of the beam. You know what? Let's just call everything E's and I's, all right? Don't make my life that much complicated, because then those don't really matter. It just makes my equations that much longer. So everything is E, A, I, and L, all right? Everything is going to be a length. L from here to here, L, and this is L here. What really matters is the geometry here that I'm interested in. So, and I'm going to include all degrees of freedom because that's just who I am. And my beams are not, could make one. Oh, let's do that. Okay. We're going to make this beam actually rigid. So I've got 1 degree of freedom less than I want. And oh, do I want to make that beam infinitely flexible? I'm just afraid that my system is going to collapse if I do that. So now I've got enough constraints here, okay? So this is A is equal to infinity. So what are my degrees of freedom? I've got, at the base, I don't worry about those degrees of freedom. I'm going to take 1, 2, and then this is actually 3. 1, 2, and 3. I'm going to do my rotations are going to be rotation here. Whoa. 1, 2, 3, 4, 5, 6. And those are actually, those are 2 rotations. And I actually don't even care about that rotation because, oh, and by the way, this isn't, yeah, this is just A is equal to infinity, okay? It's not the EA. It's the only one just for this element here, okay? And then let's just assign that as degree of freedom 7. All right, so we're going to go through. What I'm going to do is I'm going to show you all the coefficients and how we're going to compute them, but I'm not going to, you know, literally assemble the stiffness matrix in the end. So let's deal with degree of freedom 1, and let's draw the deformed shape of degree of freedom 1. So what I like to do is I first draw the regular frame. It's going to be right here. And then I'm going to impose a displacement of 1 at degree of freedom 1. And then these guys are all going to stay where they are. This one's moving over here from where it was over here. No rotations or anything, all right? So what are the forces acting here? Well, this is actually reduced. I now have to draw this guy here, and it's fixed over here, so I have no rotation here. I have this here, and I'm going to draw a deformed shape like this. This node here, I have a rigid joint, therefore it doesn't rotate here nor there. These all kind of stay the same. Actually, here's a pin, so it doesn't really matter. And then here was a pin there, but the beam is pinned to it. So right now, for this degree of freedom, nothing matters there. And this is what the deformed configuration looks like. So this is for 1. I'm actually just going to do that as the first step. The degree of freedom 2 is going to be something similar but different. Actually, yeah. I'm going to draw the frame for 2. Oh, I could just copy it. That's true. Now, this is fixed here, but I actually do have a pin here. And therefore, I take these nodes, and all these nodes are all going to stay where they are, except for this node that I'm going to translate it 1 over. What's happening here? Very important to keep track of what's happening here, especially with these that I have a pin here, and I have a pin here. So this guy's moved over, therefore I do have an elongation at this point. This guy here, this rotation is actually free to move. And so this is going to be the deformed configuration there. And interestingly, this is the deformed configuration here as well. This is a right angle, but this one doesn't have to be because it's pinned. Same thing at the top. And then everything else stays the same. Let's go to degree of freedom 1, 2, 3. I'm going to do degree of freedom 3. I'll just do it over here as well. My paper won't let me go all the way. Fixed, pinned. These nodes all stay. Now, because I've got an axially rigid beam, this whole top floor must move over to the right together. And because it's got a connection there, that node can't rotate. And same thing with this node over here, it has only moved. Now, I've got fix here, so I've got an angle here and an angle here. That's what this deformed shape is going to look like. These two guys have moved together at the same amount. And there's no rotations there, so I don't have to deal with anything. What happens here? Well, this now is the same thing. I have a pin here, so this is almost like an upside down cantilever, which is exactly the opposite almost of what I had here. And then this doesn't move. 1, 2, and 3. So where's degree of freedom 4? Oh, now we start having fun. So now we got rotations. Yes, I am trying to make this all fit into one row, but I'm not sure I'm going to be able to make that happen. Remember, because I have a pin there and a pin there, and then I have a pin here. So degree of freedom 4 is going to rotate. So this guy here, and maybe it's easier if I draw it as a, I'll draw it as a rectangle. This guy's going to have to rotate it counterclockwise this much. This is where the column now is because it's rotated 1. This is where the column is now. This guy needs to stay. This guy needs to stay, and same with this guy. So what this is going to look like is that deformed shape. This is fixed here. Whoa! There it is. I left that behind, didn't I? On purpose. This guy's here. This guy, I have a pin here. It doesn't matter what this is going to look like. And so what this is going to do, what the heck is this going to do? Ah, this is just going to stay here. If this doesn't deform and it rotates, it almost, if I have a point, because I mean, after all, this is really the point where the, you know, I should have drawn this, and this is why squares are nice, but here's what I'm going to do. I think I got myself in a bigger mess than I wanted to. And so my column is here, and therefore this guy is not going to deform at all. It's just going to rotate about that point, but that connection doesn't give you any resistance because it's pinned. Okay, I was trying to think of how the geometry was going to work out there, but that's because I had drawn the beam. I want to draw a single line there, because I literally have a pin here, so that thing can just kind of, yeah, you want to do rotation, do whatever kind of rotations you want, but I'm not going to go along with this. And because this has to stay straight, that's how everything else stays. And so this is what my deformed shape looks like. Kind of cool, isn't it? Degree of freedom 5 now. So now I have my frame. I'm going to try to fit 2 frames. Oh, I know what I can do. I can work on it and then move it over to the right if I want. So here's my frame again, fixed, pinned here. Now, and this is, I'm going to switch over to, whoops, there's a pin. Oh my gosh. Okay. This is what my system looks like, right? And degree of freedom 5 means that this joint here has rotated counterclockwise an amount of 1. I have no pins there, so everything is rotated like this. So let me draw the original one as a thin line and a straight line. Ah! Okay. And then the rotated one goes like this and like this. Now this joint here stays, this stays, and that stays like this. None of those joints rotate. So let's think about how this guy is going to deflect. This is not going to go anywhere. This here is going to do this. It's got a fixed connection here and a rotation here. It's free to rotate there because I have a pin. Same thing here. It's free to rotate. We're going to look up all these tables and find out what those forces are. And remember, I have a pin here, so this is going to do the same thing. And I think that's it for degree of freedom 5. Oh, this is so cool. All right. And then, oh, how am I going to fit 2 more in there? 6 and 7. All right. Oh, look at this. I can take this guy here now that he's done, and I'm going to move him over a little bit. Okay, good. Can I squish him in a little bit? Oh, look at that. No, stay. Oh, handy. Yes, I'm having a lot of fun with this. There it is. Move over. This makes up for my needing space when I work, but not afterwards. All right. I got way too much room. You gonna write? Pen, pen. All right. I'm gonna make this wide if I want. Oh, how did? Yes, for somebody who doesn't know how to draw straight lines, I sure am picky. But it needs to look right. It's so important because I base everything on visual. So, fine, this is good enough. All right, where's our degree of freedom 6? It's over here, so we're going to take this joint and rotate it counterclockwise to look like this. All the other joints are going to stay. Now, here's a tricky one because we have a pin, right? And so then this should be free to rotate, but no, because I've assigned a degree of freedom there. So that guy is not going to translate, or is not going to rotate. And we know it's not going to translate because degree of freedom 3 is fixed. So this guy's going to be here. We have a pin. This joint stays the way it's supposed to be. Same with this joint and everything else. So what we have here is this and this. And that's all there is to degree of freedom 6. Let's grab it. Move it. And shrink it. Oh, but I'm going to need to put forces on there. I think we're okay. Now let's do degree of freedom 7 because we're on a roll here. Except for the drawing part. I'm not. There it is. Good enough. Fixity here. Pin here. Now, what do we do? Degree of freedom 7 is going to rotate. So we have a rotation here, and everything else stays and doesn't move. Ah, well, this wasn't really there. This stays. Here we have a pin. Here we have a pin, and there's pinned. So, nothing here. This guy needs to go like that. And our pin just stays. It doesn't need to rotate. So that's all there is to this deformed shape. I don't really like how it looks, but I think it's... Here, I'm going to just redo it. A little sharper of an angle. Okay, so now we need to find out what our forces are. And we're going to have to go and pull out our table. So let's do these one at a time. And the figure that I'm going to pull out first is going to be this. So I don't know how to copy something over that's not an object. Because I can't... Oops. Can I grab this? Nope. There's got to be a way of... ink to shape. Shapes. Well, I'm just going to draw it again. There I am. So that then I can take these objects. So if... Oh, but I need to use the right pencil. Okay, let's go with red only because it stands out. So if we have this type of system where we then deform it downward, this is what our deform configuration looks like. Ouch. And it's actually good this way because then I get to draw it the way I like it. The force here and here are going to be 6 EI over L cubed. No, they're not, are they? They're going to be 12 EI over L cubed. This is going to be 12 EI over L cubed. The moment, this, I needed a force to push this down, and therefore I have a force pushing this up to keep it in place, and equal and opposite. The moment is here so that I can keep this rotation angle 0. So I have a moment in this direction. That's going to be 6 EI over L squared. And I have a moment here that's 6 EI over L squared. All right, I'm going to do is I'm going to grab these equations, or what I've drawn. I could make them a different color, but that would just be way too much work. No, no, no. That. Oh, look at that. I've just taken that with me. But no, let's not do that. I did so much work to make these look really good. So, no. I need to select something else. I don't want to select. I think I need to go here with my little arrow. Select this, guys. Now I'm going to zoom out. I had all that room to the right. And I'm going to take these over to here. So let's find out here, where is it that I need these kind of forces? Aha, right here. So I have a force here and a force here. I have a moment in this direction and a moment in this direction. I don't care what the figure over there look like. I know that I need a force to displace it here. Therefore, I have a force in the equal and opposite direction there, and this moment is there. Otherwise, this would form a straight line, and so these two moments need to keep it in the right shape, where I have 0 rotations. Just by symmetry and intuition, I have a force here and a force here, but I don't care. And I have a moment here. I don't care here because that's not part of my stiffness matrix. It's a constraint degree of freedom. So these values are going to have 6 is the moment and 12 is the forces. So this is 6 EI column over L column cubed, because I'm not going to put them in, so at least you'll know L column 1. So it could be something different. And this is 12 EI column over L column 1 cubed. This is, so if this is L1 and this is L2 and blah, 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 then this force here is going to be 12 EI column, I could even say column 1 over L column 2. So this is column 1 and column 2 cubed. And this is 6 EI column 2 over L column 2 squared. Same thing with this. This is going to be 12 EI column 2 over L column 2 cubed. And this is 6 EI column 2 over L column 2 squared. What I'm going to do is I'm going to put sign conventions right away. And I'm going to say that, find a different color. Green is the same color as red for colorblind folks, so I'm going to go blue. Okay, so this here is negative. This here is negative. This here is negative. And this here is positive. This here is positive. This here is positive. So what do you do at a joint? So what this is telling me, and I'm not going to do all of them, and I know you're going to get the pattern here. So this is degree of freedom 1. So K11 is going to be, the combination is going to be equal to 12 EI column 1 over L column 1 cubed, plus, you got to sum all the forces that correspond to degree of freedom 1, plus 12 EI column 2 over L column 2 cubed. And that one's easy. Now, what degree of freedom is this? Oh, I forgot. Another force. What's another force that's acting on here? Haha. I did this on purpose and then I forgot. We also have a force here of EA beam over L beamed. And this is there. And then this node would move to the right as we're moving that one. So this force here is also in this direction. And so to this K11, you would also add plus EA beam over L beam. See that? So this is all K11. K whatever degree of freedom that is. So K21, this is K21. So K21 is going to be equal to negative EA beam over L beam, which is, that's K2. I'm trying to figure out what is that degree of freedom. 1, 2. So K3 is 0. K31 equals 0. K41 gets fun. K41 is equal to the sum of the moments. Well, one's a plus and one's a negative. So it's going to be 6 EI column 1 over L column 1 cubed minus 6 EI column 2 over L column 2 cubed. Is it cubed or squared? It should be squared. Yep. I can erase this. I like the idea of having a pen that is erasable. So that's K41. Where's 5? K51 is 0. And K61 is... Oh! Wait! I do have a... K31 is not equal to 0. K31 is actually this value. So it's negative 12 EI column over L column 2 cubed. And then K51 to 6. K61 is equal to this moment, and it's negative 6 EI column 2 over L column 2 squared. That's it. 7. And then K71 equals 0. We got them all. All right. Well, let's move on to the next ones here. What are these forces here? Well, this is when we pull out a different equation book. Don't let me forget that there's a force. Let's put this one in right away before I forget. So this force here pushes it out. This guy will go with it. And therefore, there's a force of that. That's EA. Okay? Where am I? I see, what I need to know is what is the force here, and we can kind of already know what it looks like. There's a force that's going to be here and a force that's going to be there, and a moment that keeps it that way. And see, then here I'm like, okay, what is the direction of this moment? It's got to be in this direction. Only because the two moments have to cancel each other out. Or not. I don't know. I would think... No, they don't have to, because there is a resultant moment, actually, at that spot. But it's a way of, if this goes up, this would actually move like this, and therefore I have to apply a moment here that's going to make this angle go at a right angle. So that's why that force there is in that direction. So this is when you go to your other resources, other tables, because this one, this system here doesn't quite fit. This is that 3EI over L, which is hard to see it here. And I don't actually think that that's the one that you want to deal with. But yeah, it is the same one. Okay, because this is the same deform configuration as what we have over there. You've got a fix at one point and then free to rotate to the other. We have a deflection of one here, and therefore the force here is going to be equal and opposite to the force here. So if this is P, and that's equal to 1, I'm going to show you how I'm going to get P. Then this is also P here. If this is P there, then the moment there is P times L for equilibrium. All right, but now we got, what is P here? Well, we know that the deflection delta is equal to PL cubed over 3EI. Therefore, the force is going to be 3EI over L cubed, which is equal to the force. That's the shear force, okay? Or let's just call it a V. The moment is going to be equal to this times that, so it's 3EI over L squared. And I think you can do that by, oh my gosh, I don't have this, because I think you have to like do the one for the rotation, and I don't think I have that option, because that's why I put these into this sheet here. That's kind of like a summary of it, but it's pretty much what this looks like is so we have to find this configuration. You can find this in tables online, all right, but it's the same kind of concept that I had there. So when you have a zero deflection and a free rotation at the other end, okay, so when you start with something like this, I'm really good at tracing my own things. So then the force is going to be 3EI over L cubed, and the moment is 3EI over L squared. So let's grab this, zoom out. Oh no, and I lost it. Now I've got the whole figure, so let's do that again. What have I done? Did I move it? Yes, I did. That's what I was afraid I'd done it. Okay, so I'm going to zoom in right here. I'm going to grab it. What's there? I'm going to first move it out here. Then it's easier to deal with. Then I'm going to move it to where I want it. It's so tiny. It's okay, I can make it bigger. Is there a, oh, I wanted it over there. Yep. All right, and this is relatively easy to remember anyways. So the force here is going to be, whoa, that should be squared. Stop. Because it's just P times L, just based on equilibrium. This is also P. But we don't care. Oh, yeah. This is also 3EI over L cubed, all right? We don't care about the force here, but we know the moment is going to be 3EI over L squared. The force here, and this is column 1. This is 3EI column 1 over L column 1 cubed. Then here the force is 3EI over L column 2 cubed. This is column 2. And this is 3EI column 2 over L column 2 squared. But hey, we also have a force here, because otherwise this would have been, so we do have a force acting here that's equal to 3EI column 2 over L column 2 cubed. Signs. This is negative. This is negative because it's clockwise. This is positive, which is better be positive. This is EA beam over L beam. This is EA. Oh no, these are supposed to be in red. Sorry. So this is EA beam over L beam. EA beam over L beam. So this is negative. This is positive. That I said was positive. And this is counterclockwise, so that's positive as well. Very good. Over there, we're going to need, where did I put it? This guy here. I think we can just see it from here. And at this point, I'm hoping you're familiar with this. We got a force here and a force there, a bending moment here and a bending moment there. Here we've got a force, so we have a force here and a force there. There's nothing from the beam because it's all moving together, and there's a moment here. Nothing here, nothing elsewhere. So this is going to be the 3EI over L squared. This is 3EI over L cubed. This is 3EI over L cubed. And this is going to be 12EI over L cubed. And these two are going to be 6EI over L squared. Sign conventions. Positive. Positive. This is positive. This is, why is this force at an angle? I don't like this force at an angle. Force is in this direction, therefore it's negative. This force is negative. This force is counterclockwise, it's positive. And this force here is positive, and better be, because that's a degree of freedom that we're moving. Okay, that's it for those. And that's gonna, you can figure out what all the coefficients are. Just remember you add up all the forces. So for the beam, for the degree of freedom here is be 1, 2, and 3. Degree of freedom 7, for example, will be this value. All right, so it's a good exercise if you want, or at least just make sure that you could do this part blindly, because you're never going to have as complicated a problem as I've set up right here. Oh, I did have all this room to the right, so what I'm going to do is I'm going to grab this guy and move him over. And then let's see if I can do this like this. Can I stretch you? Yeah. Okay, there it is. And I didn't write, whoa. What have I done? Okay, I haven't saved this at all, so I'm a little nervous now. Oh, I'm in draw. This needs to be a 7 here. All right, let's draw forces here. It doesn't get easier, it only gets a little bit more complicated, okay? So for this guy to be in place, we need a force like this, otherwise that would have gone flying over there. Same thing, that angle needs to be kept in here, this in this direction and in that direction. We have forces in this direction and in this direction. These are those EI over L terms, okay? So this is rotation. So this is 4EI over L, and this is 2EI over L. This is 4EI over L. And then the forces are the 6EI over L squared. 6EI over L squared. 6EI over L squared. And same thing with here. So it's interesting. If the properties were the same, so that there's 6EI over L squared. But these are different column lengths or different column properties. If they're the same, then they will, those two shear forces will cancel out. Let's look at the signs here. Oh, and I got those from, I skipped a step here just because I kind of took it for granted. I've talked about this in a different video. When you've got this system, so it's fixed, but then you impose a rotation here and no rotation here. This is what the deform configuration looks like. Yes, mine is a little bit more accentuated than the real one. Look at that. I could almost trace. I like to accentuate just because it helps me to visualize things better. So we have a moment here of 4EI over L, and in the opposite direction, to keep it in place, is 2EI over L. It's not symmetric when you're dealing with moments. On the other hand, to keep this rotating, to keep this note when it's placed, because otherwise if you rotate here, this thing would just kind of end up here. So you need to apply a force, and I like to just draw it over here, of 6EI over L squared. And same thing, just because you have an equal and opposite force of 6EI over L squared. So what I'm going to do is I'm going to grab these guys, move them out. These are the terms that I used right down here. I'm going to put it here because I'm going to need this for this guy too. Okay. So that's what I used here. Same kind of relationships that I use there. I have, oh, this is different now. And I need to find the stiffness term here. In this, well, in all of these cases, as you can see, I have a rotation here, but then I don't have fixity at the other end. I have a pinned. So I need an even more difficult and different type of relationship. And that one is the one that I have. That's why I did all these different stiffness coefficients. I hope I have it. It's literally in a simply supported beam. There it is. Okay. So if you have a simply supported beam that is pinned and it's fixed here, it doesn't matter, and you rotate this. If I impose a rotation here, this thing is able to rotate just like a simple, oh my gosh, I made such a mess. This was this type of joint connection, and if I rotate this by an angle of 1, now this is going to look like this, but this is free to rotate as well, so this is what my deform configuration looks like. The moment here is 3EI over L, and the force here, so I need to apply a downward force here of 3EI over L squared, and therefore I need to put an equal and opposite of 3EI over L squared. Remember that we saw the 3EI over here, so it's always kind of good to remember the symmetry between the forces and the moments and the components, all right? So it's a good way of checking to making sure that you're doing it right. So what I'm going to do is I'm going to take the wrong thing. So I'm going to pick that. Pick something else. There it is. Okay, so now I'm going to grab what's here. I'm going to move it out of this box. And I go and put it where I'm supposed to be putting it. I don't think I grabbed it. Oh, I did grab it. Okay, where did you go? Where is it that I need you? I need you right here. And so that sheet that is there that we were just looking at is really the answer key to everything. So I'm going to take you, make you a little bit bigger, and move you over here. All right, now we're in a good place to go back. Oh, I didn't do before the sign convention, but I'll do it afterwards. I'm on a roll here. So now I'm going to draw the forces. I know this is a moment that needs to go this way and that way. Now the forces are going to be tricky, and it's always, you know, it's like, well, wait a minute, in which way do you do it? Well, as you can see, the force is in the same direction as the deformation. So, but it shouldn't be like upward. Oh, no. Okay. The force is going to be in this direction. Oh my gosh, I have a force here, but I didn't even worry about that degree of freedom. And I should have I should have accounted for the axial deformations of the columns and things like that, but it doesn't really matter at this point. This was just an exercise, but I should have included I'll do it in a different color. I should have included that degree of freedom and that one, and that one. All right, so those are going to be 7, 8, 9, and 10. And until now, they didn't really come into play, but they're all related to each other, because then that's where the beams come into play. This is the one case where we actually have a downward force on the beam that's resisting the rotation, but we're just going to neglect it for now, but I'm going to put it in anyway. So here I have a force in this direction, but I haven't dealt with that degree of freedom, and there's that force. And then is there a force up here? Yes, because it's got to keep it in place, and then I don't care about the force here, and there's no moment there because I don't care about it because I'm on this side of the beam, and therefore the beam isn't moving. So this term comes in because this is your K7 term. So these are all 3EI over L something, either L squared or L. So this is 3EI over L. The moments are all 3EI over L, but they're all different E's and I's, okay? So we've got 3EI. So we've got 3EI over L in all of these. The forces are 3EI over L squared. So 3EI over L squared, 3EI over L squared, 3EI over L squared, and then this is also 3EI over L squared. Let's do the sign conventions because it just otherwise, this is a lot more work than I thought it was going to be. That's positive. That force is negative. That moment is positive, which is good because this is the degree of freedom that we're moving. That force is positive. This force I don't know because I haven't decided what the sign convention is going to be for that degree of freedom, but since it's downward, we're going to say it's negative. And that's it. So we're going to add up. So for K55, you're going to add up 1, 2, and 3 moments, all right? For the shear, the force in the horizontal, you're going to have, the 2 shear forces, all right? Make sure that the signs are proper. They may or may not cancel because you may have different EIs. So then doing this by hands just kind of gets complicated. I don't need this relationship in these. I think here, because I've got back into this, this is the relationship that I need. I'm going to bring this here. So what am I doing? I've got a moment here and a moment there, a moment in that direction, a moment in this direction. And that's what's good about this exercise. Aha, look at this. Now that we start rotations, there's another degree of freedom I didn't consider. Got a force here. There's the other degree of freedom I didn't consider. There's a force here and there's a force here. And these are the ones that correspond to these rotations. So it's 4 for the moment. So this is a 4EI over L. This is a 2EI over L. This is a 4EI over L. That's a 2EI over L. And then the shear forces are 6EI over L squared. So that's 6 blah, blah, blah. This is 6 dot, dot, dot. And this is 6 and 6EI over L squared. The sign is what I'm really interested in. If this degree of freedom had been considered and I would have made it positive up, those would have been positive and negative. That's counterclockwise, so that's plus, that's a plus, that's a plus. So look, I've got 2 moments you got to add up, and I do have a shear in this degree of freedom, all right? And that's a plus, so that's for this horizontal degree of freedom. I do have a value. At this node, I have this value here, which is negative, and here I have positive. It'd be exciting to put this all together and see if I got all the sign conventions right. But again, this is really about the exercise of going through and drawing the deformed shapes. I cannot guarantee that I've done any of this right, but I'm actually confident that I've done this carefully enough. Look at this. We're almost done. So what do we have? We have a moment and a moment. We have a shear force and a shear force. This thing didn't rotate because we got a pin right there. Nothing else happened anywhere else. So this is 6EI over L squared beam. This is 6EI beam over L beam squared. Not that one. This is this force here. 6EI L beam. And then where we impose the rotation is 4EI over L. And then this is 2EI over L. I made it this far. These are going to be 2EI over L. This is 2EI over L here. For the moment is going to be, I'm going to make this moment longer, and I'm going to make it 4EI over L, 4EI beam over L beam. This is column. And then this is 6EI column 2 over L column 2 squared. And then this is 6EI beam over L beam squared. And this is 6EI beam over L beam squared. I think I got them all there. Figured I made it this far. Let's deal with those sign conventions we got. There's a positive moment. That's a positive moment, which is really good. Because that's where we apply the displacement. This is negative. This is positive if I pick those sign conventions, and that's it. We've assembled. And now you literally put in a table of K11, K21, K31, and you keep going all the way to K77. And then, and this is nice because this box here corresponds to that box. And then you got the second set from the second degree of freedom, and so on until the last degree of freedom. You put these all together, and then now you put these into a matrix, K, which is a 7 by 7, and it's got to be symmetric. And that's it. You've assembled stiffness matrix. The second part would be to do static condensation or solve the problem as you need to. I hope this was helpful. Thank you. Bye-bye.